What if the universe is hiding secrets so strange, so unimaginable, that they challenge everything we think we know about reality? Picture this: a force so powerful it pulls entire galaxies toward it, yet we can't even see it. Or a star so dense that a single teaspoon of it would weigh billions of tons. These aren't just ideas from science fiction, they're real cosmic entities lurking in the vast expanse of space, waiting to be discovered. Today, we're diving into the unknown, exploring 25 cosmic beings so bizarre, so mind-bending, that they'll make you question the very fabric of existence. From invisible forces shaping the universe to celestial objects defying the laws of physics, this journey will take you to the farthest reaches of space and beyond. So, buckle up, because what you're about to witness will leave you in awe of the universe's endless mysteries. Let's begin. Now, let's turn our attention to the first of these cosmic marvels, a force so mysterious it has baffled scientists for decades: the Great Attractor. Imagine a hidden hand in the cosmos pulling galaxies, including our own Milky Way, toward it at incredible speeds. This invisible powerhouse lies in the direction of the constellations Centaurus and Hydra, roughly 250 million light-years away. But here's the twist: we can't see it directly. The Great Attractor is shrouded by the dense plane of our galaxy, making it nearly impossible to observe with traditional telescopes. So, what exactly is it? The Great Attractor is a gravitational anomaly, a region of space where the pull of gravity is so intense that it's drawing in galaxies from across the universe. Scientists believe it's a massive concentration of matter, possibly a supercluster of galaxies, but its true nature remains elusive. What makes it even more intriguing is that it's not the only force at play. Beyond the Great Attractor lies an even larger structure called the Shapley supercluster, which may be influencing its motion. The mystery deepens when we consider how little we know about this cosmic giant. Despite decades of study, the Great Attractor continues to challenge our understanding of the universe's structure and the forces that shape it. It's a reminder that even in an age of advanced technology, the cosmos still holds secrets that defy explanation. And as we move forward in our journey, the Great Attractor serves as a perfect example of how the universe keeps us guessing, always revealing just enough to spark our curiosity, but never enough to fully satisfy it. Next, we'll explore another invisible force shaping the cosmos: dark matter halos. These ghostly structures surround galaxies, holding them together in ways we're only beginning to understand. But more on that in just a moment. Now, shifting our gaze to another enigmatic force in the cosmos, we encounter dark matter halos, structures so elusive they remain invisible to our eyes, yet their presence is undeniable. Picture a galaxy not as a solitary island of stars, but as a bustling city surrounded by an unseen network of scaffolding. These halos, made of dark matter, are the cosmic glue that holds galaxies together, preventing them from flying apart as they spin through the void. Dark matter itself is one of the universe's greatest mysteries. Unlike ordinary matter, it doesn't emit, absorb, or reflect light, making it impossible to observe directly. Yet, its gravitational influence is unmistakable. Without dark matter halos, galaxies would lack the mass needed to maintain their structure, and the universe as we know it would look entirely different. Scientists have pieced together the existence of these halos by studying the motion of stars and gas within galaxies. Stars on the outer edges of galaxies move faster than they should if only visible matter were present. This discrepancy points to the presence of dark matter, which provides the extra gravitational pull needed to explain these observations. But how do we detect something we can't see? Researchers use a variety of ingenious methods, from gravitational lensing, where the gravity of dark matter bends light from distant objects, to simulations that model how dark matter halos form and evolve over billions of years. These efforts have revealed that dark matter halos aren't just passive structures. They play an active role in shaping the cosmos, influencing the formation and distribution of galaxies across the universe. Despite these advances, dark matter remains a puzzle. What is it made of? How does it interact with ordinary matter, if at all? These questions drive ongoing experiments, from deep underground detectors searching for dark matter particles to space telescopes mapping its distribution on the largest scales. As we continue to unravel the secrets of dark matter halos, we're reminded once again of the universe's capacity to surprise and challenge us. These invisible giants are a testament to the fact that much of the cosmos remains hidden, waiting to be discovered. And with that, let's turn our attention to another cosmic marvel: quasars, the brightest objects in the universe powered by supermassive black holes. But more on that next. Now, let's journey deeper into the cosmos to uncover the brilliance of quasars, some of the most luminous and enigmatic objects in the universe. Imagine a beacon so powerful that it outshines entire galaxies, yet it's no larger than our solar system. That's the astonishing reality of quasars, cosmic powerhouses fueled by supermassive black holes at their cores. Quasars form when supermassive black holes, often billions of times more massive than our Sun, actively consume vast amounts of gas, dust, and even stars. As this material spirals into the black hole, it heats up to incredible temperatures, releasing torrents of energy in the form of light and radiation. This process creates an accretion disk, a swirling, glowing ring of superheated matter that radiates energy across the electromagnetic spectrum, from radio waves to X-rays. The result is a quasar, a celestial lighthouse so bright it can be seen from billions of light years away. But quasars aren't just dazzling cosmic phenomena, they're also invaluable tools for studying the early universe. Because they are so distant, the light we see from quasars today has traveled for billions of years, offering us a glimpse into the universe's infancy. By analyzing this ancient light, astronomers can piece together the conditions of the early cosmos, such as the formation of the first galaxies and the distribution of matter in the young universe. What makes quasars even more fascinating is their sheer energy output. A single quasar can emit thousands of times more energy than an entire galaxy, making them some of the most energetic objects known. This energy isn't just confined to their immediate surroundings. Quasars can also produce powerful jets of particles that shoot out at nearly the speed of light, extending far beyond their host galaxies. These jets can influence the evolution of galaxies and even the intergalactic medium, shaping the large-scale structure of the universe. Despite their brilliance, quasars are relatively short-lived in cosmic terms. As the supermassive black hole consumes the surrounding material, the quasar's fuel supply dwindles and its light fades. Over time, what was once a blazing quasar may become a quieter, dormant black hole, leaving behind a galaxy that has been forever altered by its presence. Quasars remind us that the universe is a dynamic and ever-changing place, where even the most extreme phenomena play a crucial role in shaping the cosmos. As we continue to study these luminous giants, we uncover not only the secrets of their formation, but also the story of how the universe itself evolved. And with that, let's turn our attention to another cosmic wonder: neutron stars, the ultra-dense remnants of supernova, where the laws of physics are pushed to their limits. But more on that next. Now, let's shift our gaze to one of the most extreme and mind-bending objects in the universe: neutron stars. Born from the explosive deaths of massive stars, these cosmic remnants are so dense that a single teaspoon of their material would weigh billions of tons on Earth. Imagine squeezing the mass of our Sun into a sphere no wider than a city. That's the staggering reality of neutron stars, where the laws of physics are stretched to their absolute limits. Neutron stars form when a massive star, typically at least 8 times heavier than our Sun, exhausts its nuclear fuel and collapses under its own gravity. The outer layers of the star are blown away in a cataclysmic supernova explosion, while the core collapses inward. What remains is a neutron star, a city-sized object with a density so extreme that protons and electrons are crushed together to form neutrons. This process creates a material so dense that it defies our everyday understanding of matter. One of the most striking features of neutron stars is their immense gravitational pull. Their gravity is so strong that it warps the fabric of space-time around them, creating effects that seem straight out of science fiction. If you were to drop an object from just a meter above a neutron star's surface, it would accelerate to millions of miles per hour before hitting the ground. This extreme gravity also causes time to slow down near the star, a phenomenon predicted by Einstein's theory of general relativity. But gravity isn't the only force at play here. Neutron stars also possess some of the most powerful magnetic fields in the universe. These fields can be trillions of times stronger than Earth's, capable of ripping apart atoms and distorting the very structure of matter. Some neutron stars, known as magnetars, take this to an even more extreme level, with magnetic fields so intense that they can cause starquakes, violent tremors on the star's surface that release bursts of energy visible across the cosmos. The bizarre physics of neutron stars doesn't stop there. Their interiors are thought to contain exotic states of matter that cannot exist anywhere else. Scientists speculate that the cores of neutron stars might be made of strange quarks, particles that are even more fundamental than protons and neutrons. These conditions push our understanding of physics to its limits, offering a glimpse into the extreme environments that exist in the universe. Neutron stars also play a crucial role in the cosmos. They are the source of some of the most energetic events in the universe, such as gamma-ray bursts and fast radio bursts. When two neutron stars collide, they create ripples in space-time known as gravitational waves, which have been detected by observatories here on Earth. These collisions also produce heavy elements like gold and platinum, scattering them across the universe and seeding the cosmos with the building blocks of planets and life. As we explore the mysteries of neutron stars, we're reminded of just how strange and wondrous the universe can be. These cosmic remnants challenge our understanding of physics, gravity, and matter itself, offering a window into the most extreme conditions nature has to offer. And with that, let's turn our attention to another cosmic enigma: black holes, where gravity becomes so intense that not even light can escape, but more on that next. Now, let's venture into one of the most fascinating and terrifying phenomena in the cosmos: black holes. These mysterious objects are regions of space where gravity is so intense that nothing, not even light, can escape their grasp. Imagine a place where the rules of physics as we know them break down, and the very fabric of reality is twisted beyond recognition. That's the realm of black holes, where the universe reveals its most extreme and enigmatic side. At the heart of every black hole lies a point of infinite density called a singularity. Surrounding this singularity is the event horizon, a boundary beyond which nothing can return. Think of the event horizon as the point of no return. Once something crosses it, it's lost to the black hole forever. This boundary isn't a physical surface, but rather a region of space where the escape velocity exceeds the speed of light, making escape impossible. One of the most mind-bending effects near a black hole is time dilation. According to Einstein's theory of general relativity, time slows down in the presence of intense gravity. If you were to observe someone falling toward a black hole, you'd see their clock ticking slower and slower as they approached the event horizon. From their perspective, time would seem normal, but to an outside observer, it would appear as though they were frozen in time. This bizarre effect challenges our understanding of time itself and highlights the strange nature of black holes. Another phenomenon that occurs near black holes is spaghettification. As an object gets closer to a black hole, The difference in gravitational pull between its near and far sides becomes so extreme that it stretches the object into long, thin strands, much like spaghetti. This process is as gruesome as it sounds, and it's a stark reminder of the destructive power of black holes. Even stars aren't safe when they venture too close. They're torn apart in a process known as a tidal disruption event, creating spectacular bursts of light and energy. But black holes aren't just cosmic destroyers. They also play a crucial role in shaping the universe. Supermassive black holes, which can weigh billions of times more than our Sun, are thought to reside at the center of most galaxies, including our own Milky Way. These giants influence the motion of stars and gas around them, helping to shape the structure of galaxies. They also power some of the brightest objects in the universe, such as quasars, by consuming vast amounts of matter and releasing enormous amounts of energy in the process. Despite their fearsome reputation, black holes are also windows into the fundamental laws of physics. They challenge our understanding of gravity, space, and time, and studying them could help us uncover new insights into the nature of the universe. For instance, the recent detection of gravitational waves, ripples in space-time caused by the collision of black holes, has opened up a new way to observe these cosmic phenomena and test our theories about how they behave. As we continue to explore the mysteries of black holes, we're reminded of just how much we still have to learn about the universe. These cosmic enigmas push the boundaries of our knowledge, offering glimpses into the most extreme and fascinating aspects of reality. And with that, let's turn our attention to another cosmic marvel, magnetars, where magnetic fields reach unimaginable strengths and unleash some of the most powerful forces in the universe. But more on that next. Now, let's shift our gaze to another cosmic powerhouse, magnetars. These extraordinary objects are a type of neutron star, but with a twist that makes them some of the most magnetic entities in the universe. Imagine a star so dense that a single teaspoon of its material would weigh billions of tons, and then add a magnetic field trillions of times stronger than Earth's. That's a magnetar, a celestial object where the forces at play are almost beyond comprehension. Magnetars are born from the remnants of massive stars that have gone supernova. When these stars collapse, they leave behind a neutron star, a city-sized object packed with the mass of our Sun. But in some cases, the neutron star's magnetic field becomes amplified to unimaginable levels, creating a magnetar. These magnetic fields are so intense that they can distort the very structure of atoms, bending and twisting them in ways that defy our understanding of physics. The effects of a magnetar's magnetic field are nothing short of catastrophic. If a magnetar were to form within a few thousand light-years of Earth, its magnetic field could disrupt electronics, erase data from hard drives, and even ionize the atmosphere. In fact, a magnetar's magnetic field is so powerful that it can cause starquakes, violent tremors on the star's surface that release bursts of energy equivalent to millions of nuclear bombs. These starquakes can send out intense flashes of X-rays and gamma rays, which, if directed toward Earth, could have devastating effects on our planet's atmosphere and technology. One of the most famous examples of a magnetar's power occurred in 2004, when a starquake on a magnetar 50,000 light-years away released a burst of gamma rays so intense that it temporarily ionized Earth's upper atmosphere. This event, known as the SGR 1806-20 burst, was so powerful that it was detected by satellites and even affected radio communications on Earth. It's a stark reminder of just how dangerous these cosmic entities can be, even from vast distances. But magnetars aren't just destructive, they're also fascinating laboratories for studying extreme physics. Their intense magnetic fields create conditions that can't be replicated anywhere else in the universe, allowing scientists to test theories about the behavior of matter and energy under extreme stress. For instance, magnetars are thought to play a role in producing fast radio bursts, mysterious high-energy signals that have puzzled astronomers for years. By studying Magnetars, we may unlock the secrets behind these enigmatic cosmic signals and gain new insights into the nature of the universe. As we explore the mysteries of Magnetars, we're reminded of the incredible diversity and power of cosmic entities. These magnetic monsters challenge our understanding of physics and remind us that the universe is full of surprises. And with that, let's turn our attention to another cosmic wanderer, rogue planets, worlds that drift through space without a star to call home. But more on that next. Now, let's venture into the realm of cosmic nomads, rogue planets. Unlike the planets in our solar system, which are tethered to the sun by gravity, rogue planets drift freely through the vast expanse of space, untethered from any star. These solitary wanderers are some of the most mysterious and intriguing objects in the universe, challenging our understanding of planetary formation and the potential for life beyond Earth. Rogue planets are thought to originate in one of two ways. Some may form around a star, just like Earth, but are later ejected from their solar systems due to gravitational interactions with other planets or passing stars. Others might form independently in the cold, dark regions of space, collapsing directly from clouds of gas and dust without ever being part of a star system. Either way, these planets are left to roam the galaxy untethered and alone. Detecting rogue planets is no easy task. Since they don't orbit a star, they don't reflect starlight, making them incredibly difficult to spot. However, astronomers have developed clever techniques to find them. One method involves gravitational microlensing, where a rogue planet passes in front of a distant star. The planet's gravity bends and magnifies the star's light, creating a temporary brightening that can be detected by telescopes. Another method relies on infrared imaging, which can pick up the faint heat signatures emitted by these cold, dark worlds. One of the most fascinating questions about rogue planets is whether they could harbor life. While they lack the warmth of a nearby star, some scientists speculate that these planets might have thick atmospheres or internal heat sources, such as radioactive decay, that could create habitable conditions beneath their surfaces. Imagine a rogue planet with a subsurface ocean, warmed by geothermal activity, where life could thrive in the absence of sunlight. It's a tantalizing possibility that expands our understanding of where life might exist in the universe. Rogue planets also offer a unique window into the chaotic processes that shape planetary systems. By studying these free-floating worlds, scientists can learn more about the forces that eject planets from their orbits and the conditions under which planets can form independently. Each discovery adds a new piece to the puzzle of how planets come to be and how they evolve over time. As we ponder the existence of these cosmic drifters, we're reminded of the incredible diversity of worlds in the universe. Rogue planets challenge our assumptions about what it means to be a planet and open up new possibilities for exploration and discovery. And with that, let's turn our attention to another interstellar mystery, Oumuamua, the enigmatic object that visited our solar system from beyond the stars. But more on that next. Now, let's shift our gaze to one of the most puzzling visitors our solar system has ever encountered, Oumuamua. This interstellar object, first detected in October 2017, zipped through our cosmic neighborhood at an astonishing speed, leaving astronomers both fascinated and baffled. Unlike anything we've seen before, Oumuamua's unusual characteristics sparked intense debates and wild theories about its origins and nature. Oumuamua's most striking feature is its shape. Unlike the typical round or irregularly shaped asteroids and comets we're familiar with, this object appeared to be elongated, almost cigar-shaped, with estimates suggesting it was about 10 times longer than it was wide. This bizarre form raised immediate questions about how such an object could form naturally. Adding to the mystery, Oumuamua exhibited no visible coma or tail, which are telltale signs of a comet. Yet, as it traveled away from the Sun, it accelerated slightly, a behavior more consistent with a comet releasing gas. Theories about Oumuamua's origins are as varied as they are intriguing. Some scientists propose it could be a fragment of a larger object, perhaps shattered by a collision in another star system. Others suggest it might be a rare type of interstellar comet, composed of materials that don't produce the typical outgassing we see in comets from our own solar system. But perhaps the most provocative idea is that Oumuamua could be an artificial object, a piece of alien technology, such as a light sail or probe, sent from another civilization. This last theory, while speculative, gained traction due to Oumuamua's peculiar acceleration and its highly reflective surface, which some argued could be consistent with a thin, metallic object. However, the majority of the scientific community remains skeptical, emphasizing the need for more data before jumping to such extraordinary conclusions. After all, as the saying goes, extraordinary claims require extraordinary evidence. What makes Oumuamua even more fascinating is its fleeting visit. By the time astronomers detected it, the object was already on its way out of the solar system, leaving little time for detailed observation. This has only deepened the mystery, as we may never know for certain what Oumuamua truly was. Yet, its brief appearance has opened up new avenues of research, inspiring scientists to develop better tools and techniques for detecting and studying future interstellar visitors. Oumuamua serves as a reminder of how much we still have to learn about the universe. Its enigmatic nature challenges our assumptions and fuels our curiosity, pushing us to ask bigger questions about what might be out there. And as we continue to explore the cosmos, who knows what other strange and wondrous objects we might encounter. With that, let's turn our attention to another cosmic mystery: dark energy, the invisible force driving the accelerated expansion of the universe. But more on that next. Now, let's venture into one of the most profound mysteries of the cosmos: dark energy. This invisible force, which makes up about 68% of the universe, is responsible for the accelerated expansion of our universe. Unlike gravity, which pulls things together, dark energy seems to push everything apart, acting as a kind of anti-gravity on a cosmic scale. But what exactly is dark energy? And why is it so difficult to study? The discovery of dark energy came as a shock to scientists in the late 1990s. While observing distant supernovae, astronomers noticed that these exploding stars were fainter than expected, suggesting they were farther away than previously thought. This led to the groundbreaking realization that the universe wasn't just expanding, it was expanding faster and faster over time. This acceleration could only be explained by the presence of an unknown force, which we now call dark energy. One of the leading theories about dark energy is that it's a property of space itself, often referred to as the cosmological constant. This idea, first proposed by Albert Einstein, suggests that empty space isn't truly empty but has an inherent energy that drives the universe apart. However, this theory raises more questions than answers. For instance, why does dark energy have the specific strength it does? If it were even slightly stronger or weaker, the universe as we know it might not exist. Another challenge in studying dark energy is its elusive nature. Unlike dark matter, which we can indirectly detect through its gravitational effects, dark energy doesn't interact with light or matter in any observable way. This makes it incredibly difficult to measure or study directly. Scientists rely on indirect methods, such as observing the large-scale structure of the universe or mapping the cosmic microwave background, to infer its presence and properties. The implications of dark energy are staggering. If the universe continues to expand at an accelerating rate, distant galaxies will eventually move so far away that they'll be beyond our observable horizon. This could lead to a future where the universe becomes a vast, empty expanse with galaxies isolated from one another. On the other hand, some theories suggest that dark energy might not be constant and could change over time, potentially altering the fate of the cosmos in ways we can't yet predict. Despite the challenges, the study of dark energy remains one of the most exciting frontiers in cosmology. It forces us to rethink our understanding of space, time, and the fundamental forces that govern the universe. As we develop new technologies and observational techniques, we may one day unlock the secrets of this mysterious force, and perhaps even discover that it's just the tip of the cosmic iceberg. With that, let's turn our attention to another vast and enigmatic region of space, the Boötes Void, a cosmic desert that defies our expectations of how the universe is structured. But more on that next. Now, shifting our gaze to one of the most puzzling regions in the cosmos, we encounter the Boötes Void, a vast and nearly empty expanse that challenges our understanding of the universe's structure. Often referred to as the Great Nothing, this region spans an astonishing 330 million light-years across, making it one of the largest voids ever discovered. Unlike the densely packed clusters of galaxies we're accustomed to, the Boötes Void contains only a handful of galaxies scattered across its immense volume. To put it into perspective, if the Milky Way were located here, we might not even know other galaxies existed. The existence of such a void raises profound questions about the universe's large-scale structure. According to the standard model of cosmology, matter in the universe is distributed in a web-like pattern, with dense filaments of galaxies separated by vast, empty regions. The Boötes Void, however, pushes this model to its limits. Its sheer size and emptiness suggest that the universe's structure might be far more complex and uneven than we currently understand. One theory about the Boötes Void's formation involves the early universe's rapid expansion during the period known as inflation. Tiny quantum fluctuations during this time could have led to regions of lower density, which, over billions of years, expanded into the massive voids we see today. Another possibility is that the void is the result of gravitational interactions, where matter was pulled away from this region by the gravitational pull of surrounding superclusters, leaving behind an empty expanse. The implications of the Boötes Void extend beyond its formation. Its existence challenges our assumptions about the uniformity of the universe and forces us to reconsider how galaxies and cosmic structures evolve. If voids like this are more common than we think, they could significantly impact our understanding of dark energy and the universe's ultimate fate. For instance, the distribution of voids might influence how dark energy drives the universe's expansion, potentially offering new clues about this mysterious force. Despite its emptiness, the Boötes Void isn't entirely devoid of interest. The few galaxies found within it are often isolated and unique, providing astronomers with a rare opportunity to study how galaxies evolve in such extreme environments. These void galaxies tend to be smaller, dimmer, and less active than their counterparts in denser regions, offering insights into how a galaxy's surroundings shape its development. As we continue to explore the Boötes Void and other cosmic voids, we're reminded of just how much we still have to learn about the universe. These vast, empty regions are not just gaps in space, they're windows into the fundamental processes that shape the cosmos. And with that, let's move on to another fascinating cosmic entity, pulsars, the rapidly spinning neutron stars that act as cosmic lighthouses, guiding us through the mysteries of space. Now, let's turn our attention to one of the most fascinating and precise objects in the cosmos, pulsars. These rapidly spinning neutron stars are the remnants of massive stars that have gone supernova, leaving behind an incredibly dense core. Imagine a star so compact that a teaspoon of its material would weigh billions of tons. Pulsars take this density to the extreme, spinning at mind-boggling speeds, some completing hundreds of rotations every single second. What makes pulsars truly remarkable is their ability to emit beams of radiation, much like a cosmic lighthouse. As they spin, these beams sweep across the sky, and if they happen to point in our direction, we detect them as regular pulses of light or radio waves. This is why they're called pulsars, short for pulsating stars. The precision of these pulses is astonishing. Some pulsars are so consistent that they rival the accuracy of atomic clocks. But pulsars aren't just cosmic timekeepers. They also play a crucial role in testing our understanding of gravity. Because of their intense gravitational fields and rapid motion, pulsars provide a unique laboratory for studying the effects of extreme gravity. For instance, when two pulsars orbit each other, they emit gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity. The first indirect detection of gravitational waves came from observing a pair of pulsars, earning the scientists involved a Nobel Prize. Pulsars also help us explore the nature of matter under extreme conditions. The intense pressure and density inside a neutron star create a state of matter that we can't replicate on Earth. By studying pulsars, scientists hope to unlock the secrets of how matter behaves in such extreme environments, shedding light on the fundamental forces that govern the universe. Interestingly, pulsars aren't just tools for scientists, they've also served as cosmic signposts. The famous Pioneer and Voyager spacecraft carried plaques and golden records that included the positions of pulsars, acting as a map to guide any potential extraterrestrial visitors to Earth. This highlights just how unique and recognizable these spinning stars are in the vastness of space. As we continue to study pulsars, they reveal more about the universe's most extreme conditions and the laws that govern it. From testing theories of gravity to acting as cosmic lighthouses, pulsars are a testament to the wonders that await us in the cosmos. And with that, let's journey further into the mysteries of space as we explore the Fermi bubbles, giant structures of gamma-ray emissions that extend from the heart of our galaxy. Now, shifting our gaze to the heart of our galaxy, we encounter one of the most enigmatic structures in the Milky Way, the Fermi bubbles. These colossal formations, stretching tens of thousands of light-years above and below the galactic center, are like two enormous balloons of gamma-ray energy. Discovered in 2010 by NASA, a Fermi Gamma-Ray Space Telescope, these bubbles are a testament to the dynamic and often violent processes occurring at the core of our galaxy. The Fermi bubbles are not just visually striking, they are also a window into the Milky Way's past. Scientists believe these structures were created by a massive burst of energy from the supermassive black hole at the center of our galaxy, known as Sagittarius, a star. This event, which likely occurred millions of years ago, could have been triggered by the black hole devouring an enormous amount of matter, releasing a torrent of energy that pushed gas and particles outward, forming the bubbles we see today. But the story doesn't end there. The Fermi bubbles also provide clues about the Milky Way's ongoing activity. The gamma rays emitted by these structures suggest the presence of high-energy particles, possibly accelerated by shock waves from the black hole's outburst. This has led researchers to speculate that similar events might have occurred multiple times in our galaxy's history, shaping its evolution over billions of years. What makes the Fermi bubbles even more intriguing is their connection to other cosmic phenomena. For instance, they overlap with a mysterious structure called the E-Rosetta bubbles, discovered by the E-Rosetta X-ray telescope. These X-ray bubbles are even larger than the Fermi bubbles, hinting at a complex interplay of energy and matter in the galactic center. Together, these structures paint a picture of a galaxy that is far from static, but rather a dynamic and ever-changing system. Studying the Fermi bubbles also helps us understand the broader universe. Similar structures have been observed in other galaxies, suggesting that the processes shaping our Milky Way are not unique. By unraveling the mysteries of these bubbles, scientists hope to gain insights into how supermassive black holes influence their host galaxies and how energy is distributed across the cosmos. As we continue to explore the Fermi bubbles, they remind us of the incredible forces at work in our galaxy and the countless secrets still waiting to be uncovered. From their origins in the heart of the Milky Way to their implications for galactic evolution, these structures are a testament to the complexity and beauty of the universe. And with that, let's venture further into the cosmos as we uncover the Hercules Corona Borealis Great Wall, a colossal structure of galaxies that challenges our understanding of the universe's large-scale structure. Now, let's turn our attention to one of the most awe-inspiring structures in the known universe, the Hercules Corona Borealis Great Wall. This colossal formation, stretching across an astonishing 10 billion light-years, holds the title as the largest known structure in the cosmos. To put that into perspective, it's so vast that it challenges our very understanding of how the universe organizes itself on the grandest scales. Discovered in 2013 by analyzing gamma-ray bursts, the Hercules Corona Borealis Great Wall is not just a random cluster of galaxies. Instead, it's a massive filament of galaxies, gas, and dark matter, woven together in a cosmic web that defies imagination. This structure is so enormous that it takes up a significant portion of the observable universe, raising questions about the limits of cosmic structures and the principles that govern their formation. What makes this Great Wall so fascinating is its sheer scale. According to the cosmological principle, the universe should appear roughly the same in all directions on large scales. Yet, the existence of such a massive structure seems to push the boundaries of this principle, suggesting that there might be more to the universe's large-scale structure than we currently understand. Scientists are still grappling with how such a colossal formation could have emerged, given the constraints of cosmic expansion and the age of the universe. The discovery of the Hercules Corona Borealis Great Wall also sheds light on the role of dark matter and dark energy in shaping the cosmos. These invisible forces are thought to play a crucial role in the formation of large-scale structures, acting as the scaffolding upon which galaxies and galaxy clusters are built. By studying this Great Wall, researchers hope to uncover more about how dark matter and dark energy influence the universe's evolution over billions of years. But the implications don't stop there. The Hercules Corona Borealis Great Wall also challenges our understanding of the early universe. Its existence suggests that the seeds of such massive structures were planted during the universe's infancy, possibly during the inflationary period just after the Big Bang. This raises intriguing questions about the initial conditions of the cosmos and how they shaped the universe we see today. As we continue to explore this monumental structure, it serves as a reminder of the universe's boundless complexity and the mysteries that still await us. From its record-breaking size to its implications for cosmology, the Hercules Corona Borealis Great Wall is a testament to the grandeur of the cosmos. And with that, let's journey further into the mysteries of space as we uncover the next cosmic entity, the Cannibal Galaxy, a fascinating example of how galaxies evolve by consuming their neighbors. Now, let's shift our gaze from the vastness of cosmic structures to a moment that sent shockwaves through the scientific community, the WOW signal. Detected on August 15, 1977, this mysterious radio signal remains one of the most compelling pieces of evidence in the search for extraterrestrial intelligence. Lasting just 72 seconds, the signal was so unusual and powerful that astronomer Jerry Amon famously circled it on the printout and wrote, "Wow." Next to it a name that has stuck ever since. The WOW signal was picked up by the Big Ear radio telescope at Ohio State University, which was scanning the skies for signs of intelligent life as part of the Search for Extraterrestrial Intelligence or SETI program. What made this signal stand out was its intensity and frequency. It was concentrated at a frequency of 1420 MHz, a range that is often considered a quiet part of the radio spectrum, making it an ideal candidate for interstellar communication. The signal also matched the expected characteristics of a transmission from an extraterrestrial source, as it was narrowband and appeared to originate from a specific point in the constellation Sagittarius. Despite its tantalizing nature, the WOW signal has never been detected again, leaving scientists puzzled. Over the years, numerous attempts have been made to explain its origin, ranging from natural phenomena like comets or distant stars to the possibility of a deliberate transmission from an advanced civilization. However, none of these explanations have been able to fully account for the signal's unique properties, keeping the mystery alive. The WOW signal has become a cornerstone in the search for extraterrestrial life, inspiring countless studies and debates. It serves as a reminder of how little we know about the universe and the potential for life beyond Earth. While the signal's origin remains unknown, it continues to fuel our curiosity and drive the quest to answer one of humanity's most profound questions: are we alone in the cosmos? As we ponder the possibilities, let's move forward to explore another cosmic marvel: the Pillars of Creation, a breathtaking region of star formation that showcases the beauty and dynamism of the universe. Now, let's turn our attention to one of the most visually stunning and scientifically significant regions in the cosmos, the Pillars of Creation. Nestled within the Eagle Nebula, approximately 7,000 light-years from Earth, these towering columns of gas and dust are a masterpiece of cosmic artistry and a window into the birth of stars. Captured in breathtaking detail by the Hubble Space Telescope in 1995, the Pillars of Creation have become an iconic symbol of the universe's beauty and complexity. The pillars themselves are colossal structures stretching several light-years in height. They are composed primarily of hydrogen gas and dust, which serve as the raw materials for star formation. Within these dense clouds, gravity pulls matter together, creating pockets of intense pressure and heat. Over time, these conditions ignite nuclear fusion, giving birth to new stars. The process is both violent and beautiful, as the intense radiation from young stars carves out cavities in the surrounding gas, sculpting the pillars into their dramatic shapes. What makes the Pillars of Creation so remarkable is not just their appearance, but also what they reveal about the life cycle of stars. They provide a snapshot of the early stages of stellar evolution, showing how stars emerge from the chaos of interstellar clouds. The region is teeming with protostars, infant stars still in the process of forming, and jets of gas ejected by young stars, offering astronomers a front-row seat to the dynamic processes that shape galaxies. However, the Pillars of Creation are not eternal. The same radiation that shapes them is also eroding them, slowly dispersing the gas and dust over time. In fact, some scientists believe that the pillars may have already been destroyed by a supernova explosion, with the light from that event yet to reach us. This adds a layer of poignancy to their beauty, reminding us that the universe is in a constant state of change. The Pillars of Creation have become more than just a scientific curiosity. They are a source of inspiration, sparking wonder and curiosity about the universe's vastness and intricacy. They remind us that even in the cold, dark reaches of space, there is a profound beauty and a story of creation unfolding on a scale that defies imagination. As we marvel at the birth of stars in the Eagle Nebula, let's journey further into the cosmos to explore the Kuiper Belt, a distant region of icy bodies that holds clues to the origins of our solar system. Now, shifting our gaze from the star-forming wonders of the Eagle Nebula, we venture to the outer edges of our solar system, where a vast, icy frontier awaits the Kuiper Belt. This distant region, stretching far beyond the orbit of Neptune, is a treasure trove of frozen remnants from the early days of our solar system. It's a place where ancient icy bodies, some as large as dwarf planets, orbit in the cold, dark reaches of space, holding secrets to how our cosmic neighborhood came to be. The Kuiper Belt is often described as a cosmic junkyard, filled with icy objects left over from the formation of the planets more than 4.5 billion years ago. These objects, ranging from small chunks of ice to massive bodies like Pluto, are like time capsules, preserving clues about the conditions and materials that existed when the solar system was young. The discovery of the Kuiper Belt in the early 1990s revolutionized our understanding of the solar system's structure, revealing that it extends much farther than previously thought. At the heart of this icy realm lies Pluto, once considered the 9th planet and now classified as a dwarf planet. Pluto's reclassification in 2006 sparked widespread debate, but it also highlighted the incredible diversity of objects in the Kuiper belt. Alongside Pluto, other dwarf planets like Eris, Haumea, and Makemake have been discovered, each with its own unique characteristics. These worlds are not just frozen rocks, they are dynamic bodies with complex geology, thin atmospheres, and even moons of their own. The Kuiper belt also plays a crucial role in understanding the origins of comets. Many of the short-period comets that occasionally grace our skies, such as Halley's Comet, are thought to originate from this region. These icy wanderers are nudged out of their orbits by gravitational interactions, sending them on a journey toward the Sun where they light up as spectacular comets. Studying these objects helps scientists piece together the history of the solar system and the processes that shaped it. One of the most exciting missions to explore the Kuiper belt was NASA's New Horizons spacecraft, which flew by Pluto in 2015, capturing stunning images of its icy surface and revealing a world far more complex than anyone had imagined. The mission didn't stop there. It went on to visit Arakoth, a small, primitive object in the Kuiper belt, providing a glimpse into the building blocks of planets. The Kuiper belt is more than just a distant collection of icy bodies. It's a window into the past, offering insights into the formation and evolution of our solar system. As we continue to explore this remote region, we uncover not only the history of our cosmic home, but also the potential for new discoveries that could reshape our understanding of the universe. With the mysteries of the Kuiper belt still unfolding, let's journey even farther into the depths of space to explore the Oort cloud, a vast, hypothetical shell of icy objects that marks the outermost boundary of our solar system. Now, as we leave the icy wonders of the Kuiper belt behind, let's venture even farther into the outermost reaches of our solar system, where the mysterious Oort cloud awaits. This vast spherical shell of icy objects is believed to encircle our solar system like a cosmic bubble, stretching nearly halfway to the nearest star. Unlike the Kuiper belt, which lies relatively close to the Sun, the Oort cloud is so distant that its existence remains largely theoretical, inferred from the behavior of long-period comets that occasionally visit our inner solar system. The Oort cloud is thought to be the birthplace of these long-period comets, which can take thousands or even millions of years to complete a single orbit around the Sun. These icy wanderers are nudged out of their distant orbits by gravitational interactions, perhaps from passing stars or the Milky Way's own gravitational pull, sending them on a journey inward. When they approach the Sun, they heat up, developing the glowing comas and tails that make them so spectacular to observe from Earth. Comets like Hale-Bopp and Hyakutake, which graced our skies in the late 20th century, are believed to have originated in the Oort cloud, offering us fleeting glimpses of this remote region. One of the most fascinating aspects of the Oort cloud is its sheer scale. It's estimated to extend from about 2,000 to as much as 100,000 astronomical units from the Sun. To put that into perspective, 1 astronomical unit is the distance between the Earth and the Sun, meaning the Oort cloud could stretch nearly a quarter of the way to Proxima Centauri, the closest star to our solar system. This immense distance makes it incredibly challenging to study directly. Unlike the Kuiper belt, which has been explored by spacecraft like New Horizons, the Oort cloud lies far beyond the reach of current technology, leaving us to rely on indirect observations and theoretical models. Another challenge in studying the Oort cloud is its sparse and diffuse nature. While it's thought to contain trillions of icy objects, they are spread out over such a vast volume of space that the region is almost entirely empty. This makes it nearly impossible to detect individual objects within the Oort cloud, even with our most advanced telescopes. Instead, scientists study the comets that originate from it, using their trajectories and compositions to infer the properties of this distant reservoir of icy bodies. Despite these challenges, the Oort cloud holds immense scientific value. It's believed to be a frozen archive of the early solar system, preserving pristine material from the time when the planets were forming. By studying the comets that come from this region, scientists can gain insights into the conditions and processes that shaped our cosmic neighborhood billions of years ago. Additionally, the Oumuamua cloud may hold clues about the formation of other star systems, as similar clouds are thought to exist around other stars. As we continue to push the boundaries of our understanding, the Oumuamua cloud remains one of the most enigmatic and intriguing regions of our solar system. Its distant, icy objects remind us of the vastness of space and the countless mysteries that still await discovery. And with that, let's turn our attention to our nearest galactic neighbor, the Andromeda galaxy, where even more cosmic wonders await. Now, shifting our gaze beyond the boundaries of our solar system, we arrive at the Andromeda galaxy, our closest galactic neighbor and one of the most awe-inspiring cosmic entities in the universe. Located approximately 2.5 million light-years away, Andromeda is a spiral galaxy, much like our own Milky Way, but on an even grander scale. With over 1 trillion stars, it dwarfs the Milky Way's estimated 200 to 400 billion stars, making it the largest galaxy in our local group. One of the most fascinating aspects of Andromeda is its structure. Like the Milky Way, it features a bright central bulge surrounded by a vast disk of stars, gas, and dust, all spiraling outward in elegant arms. These spiral arms are dotted with regions of intense star formation, where young, hot stars illuminate the surrounding gas clouds, creating a breathtaking tapestry of light. At its core lies a supermassive black hole, millions of times more massive than our Sun, exerting a powerful gravitational influence on the galaxy's stars and gas. But what truly captures the imagination is Andromeda's inevitable collision course with the Milky Way. Due to the gravitational pull between the two galaxies, they are hurtling toward each other at a speed of about 110 kilometers per second. In roughly 4 to 5 billion years, these two cosmic giants will collide in a spectacular event that will reshape both galaxies forever. While the term collision might evoke images of destruction, the process will be more like a cosmic dance. The vast distances between stars mean that direct collisions are unlikely. Instead, the galaxies will merge, their gravitational forces pulling and twisting their structures into a new, elliptical galaxy often referred to as Milkomda. This galactic merger offers a unique window into the evolution of galaxies. By studying Andromeda, scientists can better understand how galaxies grow, interact, and change over time. For instance, Andromeda's history is marked by past collisions with smaller galaxies, which have left behind streams of stars and dark matter. These remnants provide clues about how galaxies accumulate mass and evolve through cosmic mergers. The upcoming collision with the Milky Way will be a continuation of this process, offering a glimpse into the future of our own galaxy. Andromeda also serves as a vital benchmark for understanding the universe's expansion. Its proximity allows astronomers to measure distances and velocities with remarkable precision, contributing to our knowledge of dark energy and the large-scale structure of the cosmos. Additionally, Andromeda's satellite galaxies such as M32 and M110 provide insights into the dynamics of galactic systems and the role of dark matter in shaping them. As we marvel at Andromeda's beauty and complexity, we are reminded of the interconnectedness of the universe. This colossal galaxy, with its trillions of stars and swirling arms, is not just a distant neighbor but a key to unlocking the mysteries of galaxy formation and evolution. And with that, let's journey even deeper into the cosmos to explore the cosmic microwave background, the faint afterglow of the Big Bang that holds secrets of the universe's earliest moments. Now, let's turn our attention to one of the most profound discoveries in modern cosmology, the cosmic microwave background, or CMB, often referred to as the afterglow of the Big Bang. The CMB is a faint, uniform glow of microwave radiation that permeates the entire universe. This cosmic relic is essentially a snapshot of the universe as it was just 380,000 years after the Big Bang, offering us a glimpse into its earliest moments. The story of the CMB's discovery is as fascinating as the phenomenon itself. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working with a sensitive radio antenna at Bell Labs in New Jersey. They kept detecting a persistent, low-level noise that seemed to come from all directions in the sky. After ruling out all possible sources of interference, including pigeon droppings on their equipment, they realized they had stumbled upon something extraordinary. This noise was the cosmic microwave background, the oldest light in the universe, and it earned them the Nobel Prize in Physics in 1978. So, what exactly is the CMB? To understand it, we need to rewind the clock to the universe's infancy. In the first moments after the Big Bang, the universe was an incredibly hot, dense soup of particles and energy. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, allowing light to travel freely for the first time. This light, initially blazing hot, has been stretched and cooled over billions of years by the expansion of the universe, shifting from visible light to the microwave wavelengths we detect today. The CMB is remarkably uniform with a temperature of about 2.7 degrees above absolute zero. However, it's not perfectly smooth. Tiny fluctuations in temperature on the order of 1 part in 100,000 reveal the seeds of cosmic structure. These minute variations represent regions of slightly higher or lower density, which eventually grew under gravity to form the galaxies, stars, and planets we see today. In this way, the CMB is like a cosmic blueprint encoding the initial conditions of the universe. Studying the CMB has revolutionized our understanding of cosmology. It has provided strong evidence for the Big Bang theory, confirmed the universe's age at roughly 13.8 billion years, and offered insights into its composition, including the amounts of ordinary matter, and dark energy. The CMB also supports the idea of cosmic inflation, a rapid expansion of the universe in the first fraction of a second after the Big Bang, which explains the large-scale uniformity we observe. Modern missions like the Planck satellite have mapped the CMB with unprecedented precision, revealing intricate details about the universe's origins and evolution. These maps not only confirm our current understanding but also raise new questions such as the nature of dark energy and the possibility of other universes beyond our own. As we reflect on the cosmic microwave background, we're reminded of how far we've come in unraveling the mysteries of the cosmos. This faint glow, a whisper from the dawn of time, connects us to the universe's earliest moments and continues to guide our exploration of its deepest secrets. With that, let's venture further into the cosmos to uncover the Great Wall of Sloan, a colossal filament of galaxies that challenges our understanding of the universe's structure. Now, shifting our gaze to an even grander scale, we encounter the Great Wall of Sloan, one of the largest known structures in the universe. This colossal filament of galaxies stretches across an astonishing distance of approximately 1.4 billion light-years, making it a true titan of cosmic architecture. Discovered in the early 2000s through the Sloan Digital Sky Survey, this immense structure challenges our understanding of how matter is distributed across the cosmos. The Great Wall of Sloan is not just a random collection of galaxies, it's a vast network of interconnected clusters, superclusters, and voids, forming a web-like pattern that reveals the universe's large-scale structure. Imagine it as a cosmic skeleton, with galaxies strung along its filaments like beads on a string, while vast, empty regions known as voids lie between them. This intricate arrangement is a direct result of the universe's evolution, shaped by the gravitational pull of dark matter and the expansion driven by dark energy. What makes the Great Wall of Sloan so remarkable is its sheer size and complexity. It dwarfs other known structures such as the Hercules Corona Borealis Great Wall and provides a unique window into the universe's formative years. By studying its distribution of galaxies and the way they cluster together, scientists can trace the history of cosmic growth from the tiny fluctuations in the cosmic microwave background to the sprawling networks we see today. The discovery of the Great Wall of Sloan also raises intriguing questions about the limits of our universe. According to the cosmological principle, the universe should appear roughly the same in all directions on large scales. However, structures like the Great Wall of Sloan push the boundaries of this principle, suggesting that the universe may not be as uniform as we once thought. This has led to debates about whether such massive structures could hint at even larger, undiscovered features, or if they are simply rare anomalies in an otherwise homogeneous cosmos. Modern telescopes and surveys continue to map the Great Wall of Sloan in greater detail, revealing new insights into its formation and evolution. These observations not only deepen our understanding of the universe's structure, but also help refine our models of cosmology, shedding light on the roles of dark matter and dark energy in shaping the cosmos. As we marvel at the Great Wall of Sloan, we're reminded of the universe's boundless complexity and the endless mysteries it holds. This immense structure, a testament to the power of gravity and the passage of time, invites us to ponder the vastness of existence and our place within it. With that, let's journey onward to explore the Cannibal Galaxy, a cosmic predator that devours its neighbors in a dramatic display of galactic evolution. Now, let's turn our attention to a phenomenon that showcases the darker side of galactic evolution, the Cannibal Galaxy. These cosmic predators are galaxies that grow by consuming their smaller neighbors, a process that plays a crucial role in shaping the universe as we know it. Imagine a galaxy as a cosmic predator, slowly devouring its companions to grow larger and more massive over billions of years. This process, known as galactic cannibalism, is not just a dramatic spectacle but a fundamental mechanism in the life cycle of galaxies. Galactic cannibalism occurs when a larger galaxy's immense gravitational pull captures and absorbs smaller galaxies that venture too close. Over time, the smaller galaxy is torn apart, its stars, gas, and dust becoming part of the larger galaxy. This process doesn't just increase the size of the Cannibal Galaxy, it also fuels star formation and can even alter its structure, transforming spiral galaxies into elliptical ones. The Milky Way itself is no stranger to this behavior. In fact, our galaxy has a history of mergers, with evidence suggesting it has consumed smaller galaxies in the past, such as the Gaia Enceladus galaxy, which merged with the Milky Way around 10 billion years ago. One of the most striking examples of a cannibal galaxy is Messier 87, or M87, a supergiant elliptical galaxy located in the Virgo cluster. M87 has grown to its enormous size by devouring numerous smaller galaxies over billions of years. At its center lies a supermassive black hole which plays a key role in this process. As smaller galaxies are drawn in, their material spirals toward the black hole, releasing immense amounts of energy and fueling the galaxy's growth. This process also creates the spectacular jets of particles and radiation that extend far beyond the galaxy itself, making M87 a prime example of galactic cannibalism in action. The role of cannibal galaxies in the universe's evolution cannot be overstated. By consuming smaller galaxies, they help redistribute matter and energy, influencing the formation of new stars and the growth of galactic structures. This process also provides astronomers with valuable insights into the history of the universe, as the remnants of these mergers can be traced through the distribution of stars and the chemical composition of galaxies. For instance, the Milky Way's halo contains streams of stars that are remnants of past mergers, offering a glimpse into our galaxy's violent history. But galactic cannibalism isn't just about destruction, it's also about creation. The influx of gas and dust from consumed galaxies can trigger bursts of star formation, leading to the birth of new stars and planetary systems. This dynamic interplay between destruction and creation highlights the complexity of galactic evolution and the delicate balance that shapes the cosmos. As we explore the cannibal galaxy, we're reminded that the universe is a place of constant change, where even the largest structures are shaped by the interactions of their smaller counterparts. This process, while seemingly violent, is a natural part of the cosmic dance that has been unfolding for billions of years. With that, let's move on to our next cosmic wonder, the Tarantula Nebula, a dazzling star-forming region that showcases the universe's creative power. Now, let's shift our gaze to a cosmic marvel that embodies the universe's creative brilliance, the Tarantula Nebula. Nestled within the Large Magellanic Cloud, a satellite galaxy of the Milky Way, this colossal star-forming region is one of the most active and luminous in our galactic neighborhood. Spanning over 600 light-years, the Tarantula Nebula is a sprawling nursery of stars, where the raw materials of the cosmos come together to ignite the birth of new suns. At the heart of the Tarantula Nebula lies R136, a cluster of some of the most massive stars ever discovered. These stellar giants, some weighing over 200 times the mass of our Sun, burn with an intensity that defies imagination. Their fierce radiation and powerful stellar winds sculpt the surrounding gas and dust into intricate filaments and bubbles, creating a breathtaking tapestry of light and shadow. This intense activity not only shapes the nebula but also drives the formation of new stars, as shockwaves from supernova and stellar winds compress nearby gas clouds, triggering further star birth. One of the most fascinating aspects of the Tarantula Nebula is its role as a cosmic laboratory. Astronomers study this region to understand the processes that govern star formation, particularly in environments rich in heavy elements. The nebula's proximity, at just 160,000 light-years from Earth, makes it an ideal target for observation. Telescopes like the Hubble Space Telescope have captured stunning images of the Tarantula Nebula, revealing its intricate structures and the dynamic interplay of its stellar inhabitants. The Tarantula Nebula is also home to one of the most dramatic events in the universe, supernova. When massive stars exhaust their fuel, they explode in a cataclysmic release of energy, scattering their enriched material into space. These explosions seed the surrounding region with elements essential for the formation of planets and life, making the Tarantula Nebula a crucial player in the cosmic cycle of creation and destruction. In fact, one of the most famous supernova in recent history, supernova 1987A, occurred in the outskirts of the Tarantula Nebula, providing astronomers with invaluable insights into the final stages of stellar evolution. Beyond its scientific significance, the Tarantula Nebula captivates with its sheer beauty. Its glowing clouds of hydrogen gas, illuminated by the light of newborn stars, create a visual spectacle that has inspired awe and wonder for centuries. This nebula serves as a reminder of the universe's boundless creativity, where even in the vastness of space, the processes of birth and renewal continue unabated. As we marvel at the Tarantula Nebula, we're reminded that the universe is not just a place of darkness and mystery, but also a canvas of light and life. This star-forming region, with its intense activity and stunning visuals, offers a glimpse into the forces that shape galaxies and the stars within them. With that, let's journey onward to our next cosmic wonder, the Whirlpool Galaxy, a stunning spiral galaxy that reveals the intricate dance of galactic interactions. Now, let's turn our attention to a cosmic masterpiece that showcases the elegance of galactic interactions, the Whirlpool Galaxy, officially known as Messier 51. This stunning spiral galaxy is located approximately 23 million light-years from Earth in the constellation Canes Venatici. What makes the Whirlpool Galaxy truly remarkable is its close encounter with a smaller companion galaxy, NGC 5195, creating a breathtaking display of gravitational forces at work. The whirlpool galaxy's spiral arms are a defining feature, swirling outward in a mesmerizing pattern of stars, gas, and dust. These arms are not just beautiful, they are also regions of intense star formation where the compression of gas clouds triggers the birth of new stars. The galaxy's bright core, packed with older stars, contrasts sharply with the vibrant blue clusters of young stars scattered along its arms, offering a snapshot of stellar evolution in action. What sets the whirlpool galaxy apart is its interaction with its smaller companion. The gravitational pull between the two galaxies has distorted their shapes, stretching out streams of stars and gas in a cosmic dance. This interaction has also triggered bursts of star formation in both galaxies, as the gravitational forces compress gas clouds, igniting the birth of new stars. The whirlpool galaxy's companion, NGC 5195, is no passive partner. Its own structure has been warped by the encounter, creating a dynamic interplay that astronomers study to understand how galaxies evolve over time. One of the most fascinating aspects of the whirlpool galaxy is what it reveals about galactic dynamics. The interaction between these two galaxies provides a real-time example of how galaxies grow and change through mergers and collisions. Over billions of years, such interactions can lead to the formation of larger, more complex galaxies, reshaping the cosmic landscape. The whirlpool galaxy and its companions serve as a living laboratory, offering insights into the processes that drive galactic evolution. The whirlpool galaxy is also a favorite among amateur and professional astronomers alike. Its relatively close proximity and face-on orientation make it one of the most photographed galaxies in the night sky. Through telescopes, its intricate spiral structure and the delicate filaments connecting it to its companion are clearly visible, offering a glimpse into the beauty and complexity of the universe. As we marvel at the whirlpool galaxy, we're reminded of the interconnectedness of the cosmos. This stunning spiral galaxy, with its graceful arms and dynamic interactions, teaches us about the forces that shape galaxies and the ongoing dance of creation and transformation in the universe. With that, let's continue our journey to explore another cosmic wonder, the Ring Nebula, a celestial object that showcases the final stages of a star's life cycle. Now, shifting our gaze to a celestial object that marks the final act of a star's life, we encounter the Ring Nebula, officially catalogued as Messier 57. This stunning planetary nebula lies approximately 2,300 light-years away in the constellation Lyra. Unlike the sprawling galaxies we've explored, the Ring Nebula is a much smaller but no less fascinating cosmic entity, offering a glimpse into the dramatic end stages of stellar evolution. The Ring Nebula's most striking feature is its iconic ring-like shape, a glowing halo of gas and dust that appears almost perfectly circular when viewed from Earth. This structure is the result of a dying star shedding its outer layers into space, creating a luminous shell of ionized gas. At the center of the nebula lies a white dwarf, the dense remnant of the star that once shone brightly. This tiny, hot core emits ultraviolet radiation, causing the surrounding gas to glow in vibrant hues of blue, green, and red, making the Ring Nebula a favorite target for both amateur and professional astronomers. What makes the Ring Nebula particularly intriguing is the process that formed it. When a star similar in size to our Sun exhausts its nuclear fuel, it expands into a red giant, shedding its outer layers in a series of powerful stellar winds. These expelled layers form a glowing shell around the star, while the core collapses into a white dwarf. Over time, the expanding shell of gas cools and disperses, leaving behind the delicate, ring-like structure we see today. This process, though marking the end of a star's life, also enriches the surrounding space with heavy elements like carbon and nitrogen, which will eventually become the building blocks for new stars and planets. The Ring Nebula's intricate structure also provides valuable insights into the dynamics of planetary nebulae. observations reveal that the nebula is not a perfect sphere but rather a torus or donut-shaped structure with a central white dwarf illuminating the inner regions. The outer edges of the nebula are fainter and more diffuse, creating the illusion of a ring when viewed from our perspective. This complex geometry challenges our understanding of how such nebulae form and evolve, making the Ring Nebula a key object of study for astronomers. Beyond its scientific significance, the Ring Nebula captivates with its sheer beauty. Its vivid colors and symmetrical shape make it one of the most photographed objects in the night sky. Through telescopes, the nebula's intricate details come to life, offering a breathtaking view of the delicate balance between creation and destruction in the cosmos. As we reflect on the Ring Nebula, we're reminded of the cyclical nature of the universe. This celestial object, born from the death of a star, serves as a poignant reminder that even in the end there is beauty and purpose. With that, let's turn our attention to the final cosmic entity on our journey, the Triangulum Galaxy, a smaller yet equally fascinating member of our local group. Now, as we venture into the final chapter of our cosmic journey, we arrive at the Triangulum Galaxy, a captivating spiral galaxy that holds its own unique place in the local group. Known formally as Messier 33, this galaxy is located approximately 3 million light-years away, making it one of our closest galactic neighbors. While it may be smaller than the Milky Way and Andromeda, the Triangulum Galaxy is no less remarkable, offering a wealth of insights into the processes that shape galaxies and the universe at large. The Triangulum Galaxy is a classic example of a spiral galaxy, with its graceful arms winding outward from a bright central core. These arms are studded with vibrant star-forming regions where clouds of gas and dust collapse under gravity to ignite new stars. One of the most famous of these regions is NGC 604, a massive stellar nursery that rivals the Orion Nebula in our own galaxy. These areas of intense star formation not only light up the galaxy, but also provide astronomers with a front-row seat to the birth of stars and planetary systems. What sets the Triangulum Galaxy apart is its relationship with the Milky Way and Andromeda. As the third largest member of the local group, it plays a crucial role in the cosmic dance of galaxies. While it is gravitationally bound to Andromeda, the Triangulum Galaxy is also on a slow but inevitable collision course with its larger neighbor. In the distant future, these two galaxies will merge, creating a new, larger galaxy in a process that mirrors the eventual fate of the Milky Way and Andromeda. This interconnectedness highlights the dynamic nature of the universe, where galaxies are not isolated islands but part of a vast, evolving web. Despite its smaller size, the Triangulum Galaxy is a treasure trove of astronomical phenomena. Its relatively low density of stars compared to the Milky Way and Andromeda allows for clearer observations of its structure and composition. This has made it a prime target for studying the distribution of gas, dust, and dark matter within spiral galaxies. Additionally, its proximity to Earth provides a unique opportunity to observe the life cycle of stars and the processes that drive galactic evolution. The Triangulum Galaxy also serves as a reminder of the diversity within the cosmos. While it may not be as massive or as well known as its larger counterparts, it is a testament to the beauty and complexity of the universe. Its delicate spiral arms and glowing star-forming regions offer a glimpse into the intricate processes that shape galaxies, while its role in the local group underscores the interconnected nature of cosmic structures. As we conclude our exploration of the Triangulum Galaxy, we reflect on the incredible journey through 25 cosmic entities that have challenged our understanding of the universe. From the mysterious Great Attractor to the stunning Ring Nebula, each of these entities has revealed a different facet of the cosmos, reminding us of its vastness, complexity, and beauty. Thank you for joining us on this journey through the wonders of space. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. Until next time, keep looking up. As we wrap up this cosmic odyssey, let's take a moment to reflect on the incredible diversity and mystery of the 25 cosmic entities we've explored. From the enigmatic Great Attractor pulling galaxies toward it with unseen force to the haunting beauty of the Ring Nebula, each entity has unveiled a unique chapter in the story of the universe. We've marveled at the raw power of black holes, the delicate dance of rogue planets, and the explosive brilliance of quasars. These cosmic wonders remind us that the universe is not just vast but endlessly varied, filled with phenomena that challenge our understanding and ignite our curiosity. The journey through these entities has shown us that the cosmos is a place of both order and chaos, where galaxies collide, stars are born, and mysterious forces like dark energy shape the very fabric of reality. Each discovery raises new questions, pushing the boundaries of what we know and inspiring us to look deeper. Whether it's the eerie silence of the Boötes void or the dazzling star-forming regions of the Tarantulum Nebula, these cosmic entities are a testament to the beauty and complexity of the universe. But this is just the beginning. The universe is a treasure trove of mysteries waiting to be uncovered, and every observation, every discovery, brings us closer to understanding our place in the grand cosmic tapestry. If you've enjoyed this journey through the wonders of space, don't forget to share your thoughts in the comments below. What cosmic entity fascinated you the most? Let's keep the conversation going, and if you haven't already, hit that subscribe button and ring the notification bell so you never miss out on our next cosmic adventure. Together, let's continue exploring the infinite wonders of the universe. Until next time, keep your eyes on the stars and your curiosity alive.